This video is about the change in arithmetic and geometric sequences. This is AP Precalculus Topic 2.1. If you appreciate this content, don't forget to hit the like button. A sequence is a function from the whole numbers to the real numbers. This means that we are only able to plug in whole numbers, 0, 1, 2, 3, etc., into a sequence, but we can get any real number as the output. As a result, when we graph a sequence, we will have points, but we cannot connect them together to form a line or a curve. Example 1. Consider the sequence defined by an equals 4n minus 3. Find a1 and a7. a1 will equal 4 times 1 minus 3. So a1 is 1. a7 will equal 4 times 7 minus 3. So that's 28 minus 3, which is 25. In this course, we will study two important types of sequences, arithmetic and geometric. Let's start with arithmetic sequences. In arithmetic sequences, successive terms have a common difference or constant rate of change. For example, in this sequence, each successive term is increasing by 3. So 3 is the common difference, and it is denoted by the letter D. For an arithmetic sequence, you can find the nth term, an, using this formula, an equals ak plus d times n minus k. In this formula, d is the common difference I mentioned earlier, and ak is term k, usually a term that you know. Note that arithmetic sequences behave a lot like linear functions, except they are not continuous. Consider the arithmetic sequence defined by an equals 3n plus 1. Here are the first 5 terms of the sequence, starting with term 0. And here are the 3 values that fit on the graph. Resist the temptation to connect the dots. That doesn't work for sequences. Example 2. For each of the following, determine if the sequence could be arithmetic. If yes, identify the common difference. Let's start with part A. Sn equals n squared minus 3. Here are the first 3 terms, starting with term 1. From the first term to the second term, there's a difference of 3. But then from the second term to the third term, there's a difference of 5. So this cannot be arithmetic because there's not a common difference. For part B, consider the sequence defined by Sn equals 6 minus 2n. Here are the first 3 terms. This sequence is arithmetic because we see a common difference between successive terms. The common difference is negative 2, so d equals negative 2. Look at the sequence given for part C. From negative 7 to negative 2, that's an increase of 5. And then from negative 2 to 3, that's another increase of 5. From 3 to 8, that's 5 more. And from 8 to 13, that is 5 more. So yes, this is arithmetic because there is a common difference of 5 between successive terms. D equals 5. On part D, notice how the signs are switching back and forth. Positive, negative, positive, negative, positive. When the sign changes more than once, there's no way that this is going to be arithmetic. Also, we see that from 1 to negative 2, that's a difference of negative 3, but from negative 2 to 3, that is a difference of 5. So, no common difference. Example 3. Let an be an arithmetic sequence with a3 equals 8 and d equals negative 3. Find an expression for an and use the expression to find a12. All arithmetic sequences can be modeled by this equation, where ak is a value that you know, which in this case will be a3, and d is the common difference, which we are given as negative 3. So we can begin by writing an equals. And I think I'll show this extra step by just writing A3. And then we have negative 3 times n minus k. That's going to be n minus 3. But we know that A3 is 8. So when you get comfortable, you can skip this first step and go straight to what I am about to write now. So an is equal to 8. Instead of putting plus negative 3, let's just put 8 minus 3 times n minus 3. This is a perfectly good expression for an, but sometimes people like to distribute the negative 3, so I'm going to keep going just to show you the other form. Make sure if you distribute negative 3, not just 3. So negative 3 times n is going to be minus 3n, and then negative 3 times negative 3 is positive 9. Combining like terms gives us another expression for an. Now let's find A12. So A12, and I think I'll use our last expression. A12 will equal negative 3 times 12 plus 17. So A12 will equal negative 36 plus 17. So A12 is negative 19. Example 4. Let an be an arithmetic sequence with A2 equals 7 and A6 equals 9. Find an expression for an and use the expression to find A24. For an arithmetic sequence, an equals ak plus d times n minus k. We do not know the common difference d. However, we are given two different values of the sequence. We can put one here and one here, and that will allow us to solve for d. Let's put the one with the larger subscript in the front. So let's put A6 here and A2 here. So far we have A6 equals A2 plus d times n minus k will be 6 minus 2. We know that A6 is 9, so let's put that in there, and A2 is 7, so that goes right there. Now, for d times 6 minus 2, that's d times 4, which I will write as 4d. Subtracting 7 from both sides, we get 2 is equal to 4d, and dividing both sides by 4, we get 1/2 is equal to d. Now that we know the common difference, we can go back and write a formula for an using either one of these two given values. Let's just use the smaller one. So an will equal A2 plus d, which is 1/2, times n minus 2. But A2 is 7, so an is equal to 7 plus 1/2 times n minus 2. This is a valid expression for an. Let's use it to find A24. To find A24, we just plug in 24 for n. So we get 7 plus 1/2, 24 minus 2, which means A24 will equal 7 plus 24 minus 2 is 22. Half of that is 11. So A24 is 18. Quick side lesson. We just found the expression an equals 7 plus 1/2 times n minus 2. But on a multiple choice question, sometimes it'll be written in another way, so let's just review the other form that you might see. Sometimes they distribute this d that's in the front. So if we do that, then we will have an equals 7 plus 1/2 n minus 1. Then combining these like terms, we get an is equal to 1/2 n plus 6. So this is the other version that you might see. Example 5. Several terms of the arithmetic sequence an are shown above. Find an expression for an and use the expression to find a17. The first 5 terms of the sequence are 8, 6, 4, 2, 0. We can see there is a common difference of -2. In other words, d is equal to -2. We can use any one of these values to write an expression for an. I'm going to use a1 equals 6, but any of these would work. So using the model we've been using before for arithmetic sequences, we know that an will equal a known value, so I'll just go ahead and write a1 for now, plus the common difference, which is -2, times n minus k, in this case n minus 1. But we know that a1 is 6, so feel free to skip this step and go straight to an is equal to 6 minus 2 times n minus 1. So this is an expression for an. There are many others. Now let's use this expression to find a17. a17 will equal 6 minus 2 times 17 minus 1. So a17 will equal 6 minus 2 times 16. 2 times 16 is 32. So a17 will equal 6 minus 32. So a17 is -26. Now let's talk about geometric sequences. A geometric sequence is one where successive terms have a common ratio. For example, 2 times 3 is 6, and then 6 times 3 is 18, and then 18 times 3 is 54. So guess what? The common ratio is 3, and it is denoted by r. By the way, they call it a common ratio instead of a common multiplier or something, because you get the common ratio by dividing each term by the term before. 6 divided by 2 is 3. 18 divided by 6 is 3. You can find the nth term gn of a geometric sequence using the equation gn equals gk times r to the n minus k power, where r is the common ratio and gk is term k. Notice that geometric sequences behave like exponential functions, except they are not continuous. Consider the geometric sequence given by this expression. Let's find the first few terms and graph them. Let's start with term 0. If we plug in 0 for n, 1/2 to the 0 power is 1. 1 times 8 is 8. So g0 would be 8. So that's going to be right here. We can find g1 by plugging 1 in for n. So that just leaves 1/2 times 8, which is 4. Also, a common ratio of 1/2 means that you can get successive terms by multiplying by 1/2. So using that, we know the next term is going to be 2, and the next term is going to be 1. So the first 4 terms look like this. Example 6. For each of the following, determine if the sequence could be geometric. If yes, identify the common ratio. Part A, Sn equals 3n squared. Let's generate the first few terms starting with term 1. If we plug in 1 for n, then we just have 3 times 1, which is 3. What about term 2? This will now become 3 times 2 squared. That's 3 times 4, which is 12. What about term 3? 3 squared is 9, times 3 is 27. This should be enough for us to answer the question. From 3 to 12, the ratio is 4. 3 times 4 is 12. But from 12 to 27, the ratio is, well, it's not 4. Because 4 times 12 is 48, not 27. and that's all that matters. No, part A is not geometric. Let's do the same thing for part B. Sn equals 4 times 2 to the n minus 1 power, starting with term 1. If we plug in 1 for n, 1 minus 1 is 0, 2 to the 0 power is 1, 4 times 1 is 4. So how about term 2? Plugging in 2 for n, we have 2 minus 1, which is 1. So that's just 4 times 2, which is 8. And what about term 3? If we plug in 3 for n, 3 minus 1 is 2. 2 squared is 4. 4 times 4 is 16. This should be enough to check. 4 times 2 is 8, and 8 times 2 is 16. Yes, this sequence is geometric with a common ratio of 2. Scan across the terms for part C. Notice they are getting bigger and smaller, and bigger and smaller, and bigger and smaller, and bigger. That does not happen for a geometric sequence. It either keeps growing or it keeps shrinking. So we know the answer is no. Also, if there was going to be a common ratio, it would come from 3 divided by 1, which is 3. So that's the first ratio. But then 2 divided by 3 is 2/3. So these are not the same, so not geometric. Looking at part D, the second term divided by the first term is going to be negative 1/2. And then the third term divided by the second term is also negative 1/2. And then the fourth term divided by the third term is negative 1/2. And then the fifth term divided by the fourth term, one more time, is negative 1/2. So yes, this is geometric with a common ratio of negative 1/2. Example 7. Let Gn be a geometric sequence where G1 equals 12 and R equals 2. Find an expression for Gn and use the expression to find G4. Remember, here's the model for a geometric sequence. So we can find an expression for Gn using the given value G1. That's our GK. So G1 times the common ratio of R, which is 2, I'm going to put that in parentheses, to the n minus k power. So that'll be to the n minus 1 power. But we know that G1 is 12. So this will become Gn is equal to 12 times 2 to the n minus 1 power. This is an expression for Gn. Now we can use it to find G4. G4 will equal 12 times 2 to the 4 minus 1 power. So G4 will equal 12 times 2 to the third power. 2 to the third power is 8. So G4 will equal 12 times 8. G4 is 96. Example 8. Several terms of the geometric sequence Gn are shown above. Find an expression for Gn and use the expression to find G10. Here are the first 4 terms labeled. These will be enough. Notice that we can get from one term to the next by multiplying by 1/2. That means that the common ratio is 1/2. This is the model for a geometric sequence, and now we know that R is 1/2. We can just pick any one of these terms and plug it into the formula to find an expression for Gn. I'm going to use G at 1 equals 4, but any of these would work. So Gn will equal G1 times the common ratio of 1/2 to the n minus k power. In this case, that's going to be n minus 1. Substituting 4 for g1, we have this expression for gn. Now let's use it to find g10. g10 should equal 4 times 1/2 to the 10 minus 1 power. So that means g10 should equal 4 times 1/2 to the 9th power. 2 to the 9th power is 512. Therefore, 1/2 to the 9th power is 1 over 512. But 4 times 1 over 512 is 4 over 512. 4 over 512 reduces down to 1 over 128. So this is the simplified value of g10. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.